Namaskar. I discuss the physical theorems on physical's meaning of the Hamiltonian's theorem for conservative scalenomic system. The Hamiltonian urge represents both a constant of motions and total energy. For conservative economic system, the Hamiltonian urge may represent a constant of motion but does not represent the total energy. Proof: the Hamiltonian urge is defined by urge is equal to summation of Pj Qj dot minus L, where L is the Lagrangian of the system and Pj is equal to minus dou L by dou Qj dot is the generalized momentum. This implies from Lagrange's equations of motion that Pj dot is equal to d by dt of dou by L by dou by Qj is equal to dou by L by dou by Qj. Differentiating equation 1 with respect to t, therefore dh by dt is equal to my summation of Pj Qj dot plus summation of Pj Qj double dot minus summation of dou L by dou Qj dot minus summation of dou L by dou Qj double dot minus dou L by dou T. On using equation 2 and 3 in equation 4, we radially obtain dh by dt is equal to minus dou L by dou T. Now, if L does not contain time t explicitly, then from equation 5 we have dh by dt is equal to 0. This shows that S represents constant of motions. However, the condition L does not contain time t explicitly will be satisfied by neither the kinetic energy nor the potential energy involved time t explicitly. Now, there are two cases that the kinetic energy T does not involve time t explicitly. For the conservative scalenomic system, in case of conservative system, when the constants are scalenomic, then the kinetic energy T is independent of time t and the potential energy V is only functions of coordinates. Consequently, the Lagrangian L does not involve time t explicitly, and hence from equation 5 the Hamiltonian urge represents a constant of motions. Further, for scalenomic system, we know the kinetic energy is a homogeneous quadratic functions of generalized velocity t is equal to summation of ajk qj dot qk dot. Hence, by using Eyelash theorem for the homogeneous quadratic functions of generalized velocities, we have summation of qj dot dou by t by dou by qj dot is equal to 2t. From conservative system, we have Pj is equal to dou by L by dou by Qj dot is equal to dou by T by dou by Qj dot. Using equation 7 and 8 in the Hamiltonian urge, we get H is equal to 2T minus T minus V, H is equal to T plus V is equal to E, where E is the total energy of the system. Equation 9 shows that the conservative scalenomic system, the Hamiltonian urge represents the total energy of the system. For conservative economic system, in the case of conservative economic system, the transformation equation do not involve time t explicitly. Though sometimes the kinetic energy may not involve time t explicitly. Consequently, neither T nor V involves T, hence L does not involve time t. Hence, in such cases, the Hamiltonians may represent the constant of motions. However, in general, if the system is conservative and rheonomic, the kinetic energy is quadratic functions of generalized velocities and is given by T is equal to summation of Ajk Qj dot Qk dot plus summation of Aj Qj dot plus A, where Ajk is equal to summation of 1 by 2 mi da by ri by da by Qj da by ri by da by Qk. Aj is equal to summation of mi da by ri by da by Qj da by ri by da by T, and A is equal to summation of 1 by 2 mi da by ri by da by T square. We see from the equation 10 that each term is homogeneous functions of generalized velocities of degree 2, 1 and 0 respectively. On applying Eyelash theorem for the holonomic functions, homogeneous function to each term on the right hand side, we readily get summation of Qj dot da by T by da by Qj is equal to 2T plus T1, where T2 is equal to summation of Ajk Qj dot Qk dot T1 is equal to summation of Aj Qj dot T0 is equal to A. Are homogeneous functions of generalized velocity of degree 2, 1 and 0 respectively. Substituting equation 12 in the Hamiltonian one, we obtain H is equal to T2 minus T0 plus V, showing that the Hamiltonian H does not represent the total energy. Thus, for the conservative rheonomic system, H may represent the constant of motions but does not represent total energy. Next, cyclic coordinate in Hamiltonian. Prove that a coordinate which is cyclic in the Lagrangian is also cyclic in the Hamiltonian. We know that coordinate which is absent in the Lagrangian is called cyclic coordinate. Thus, if Qj is cyclic, then da by L by da by Qj is equal to 0. Hence, the Lagrangian equations of motions reduces to d by dt of da by L by da by Qj dot is equal to 0. Therefore, Pj dot is equal to 0, where Pj dot is equal to da by L by da by Qj is the generalized momentum. However, from Hamilton's canonical equations of motion, we have Pj is equal to minus dou h by dou Qj. Equation 1 and 2 gives dou h by dou Qj is equal to 0. This shows that the coordinates Qj is also absent in the Hamiltonian, and hence consequently it is also cyclic in H. Thus, a coordinate which is cyclic in the Lagrangian is also cyclic in the Hamiltonian. Next example, describe the motion of a particle of mass m moving near the surface of the earth under the earth's constant gravitational field by Hamilton's procedure. Solutions for proof. Consider a particle of mass m moving near the surface of the earth under the earth's constant gravitational field. Let x, y, z be the Cartesian coordinate of the particle, projectile z being vertical. Then the Lagrangian of the particle is given by L is equal to 1 by 2 m x dot square plus y dot square plus z dot square minus mgz. We see that the generalized coordinates z, x and y are absent in the Lagrangian. Hence, they are the cyclic coordinate. This implies that any change in these coordinate cannot affect the Lagrangian. This implies that the corresponding generalized momentum is conserved. In this case, the generalized momentum is the linear momentum and is conserved. P phi px is equal to mx dot is equal to constant, py is equal to my dot is equal to constant, pz is equal to mz dot is equal to constant. This shows that the horizontal momentum of the horizontal component of the momentum are conserved. The Hamiltonian of the particle is defined by H is equal to summation of Pj Qj dot minus L. H is equal to Px x dot plus Py y dot plus Pz z dot minus 1 by 2 m x dot square plus y dot square plus z dot square plus mgz. Eliminating x dot y dot z dot between comp equations 2 and 3, we get H is equal to 1 by 2 m px square plus py square plus pz square plus mgz. The Hamilton's equations of motions gives px dot is equal to minus dou h by dou x is equal to 0, px dot is equal to minus dou h by dou y is equal to 0, pz dot is equal to minus dou h by dou z is equal to minus mgz, and x dot is equal to dou h by dou px is equal to px by m, y dot minus dou h by dou px dou py is equal to py divided by m, z dot is equal to dou h by dou pz is equal to pz by m. From this set of equation we obtain x double dot is equal to 0, y double dot is equal to 0, z double dot is equal to minus g. These are the required equations of motions of the projectile near the surface of the earth.